Let's talk about singly linked lists. How hard can they be? Let's look at the first cut. Here is an S list with a constructor, a destructor, and like I said, a find where you get a value and return a pointer into the list to where that value was found, if it was found, null otherwise, and then push front, put a new element into the list. My data structure is going to be what I showed on the previous screen. Each node has a T and a pointer to the next node. And I'm going to have an atomic node star head that I've initialized to null putter. Now, if you're wondering whether to make something atomic, remember this good rule of thumb. If you want to avoid race conditions, which you must to avoid undefined behavior, to avoid race conditions, make sure every mutable shared object in the system is either protected with a lock or atomic. There are a few other tools if you want to get fancy with semaphores, but 95+% of the time it should be protected by a mutex, or in a few cases, made atomic. Head, as we were going to see, is a shared mutable variable. Therefore, it had better be protected with a mutex, which we're not going to do just because we want to use atomics, or atomics, which is now what we're going to do. And by the way, I'm going to delete copying because I don't want to worry about copying S lists. Make this a move-only type. You'd have to write the move. The constructor is easy. The default equals default would do the right thing. And that's because we've already got the head becoming null. That's a valid list. We do not need any synchronization on the constructor because even on the same thread that's constructing the object, it's not legal to make member function calls on an object until its lifetime begins, which is when its constructor ends. So it's not even legal in a reentrant case for you to be making member function calls externally on an object before it's been fully constructed. That's same is true concurrently. That means you don't need to worry about that. Constructors run in isolation. Peter.
Why did you declare it at all?
Because I wanted to make that point.
Okay.
Now let's look at the destructor. The destructor, which we've all written 100,000 times, is load head. Now remember, that's reading an atomic variable, and I want a raw pointer, so I'm going to go head.load. And while first, unlink the first one, delete it, and then recurse, or then iterate. So you're going to go through the list and delete each node as you go. There are also no concurrency issues here. Destructors also run in isolation. This is a surprise to people, but it's actually very easy when you realize, oh yeah, of course. Because if somebody tries to use an object after destroying it, that's the caller's bug. It's not the bug in the guy who wrote class widget. It's like, well, you destroyed the widget. You should stop using it, right? If you have code that could run concurrently with this destructor, it could just it's a race. It could have as easily run after. It's the same thing. You're not allowed to use, it's a bug in the caller, to write code that tries to use an object on another thread while it's being destroyed, after its lifetime ends, which is the beginning of the destructor. Nothing new here. That's the way it's always been in C++. We're just adding concurrency. Same rule applies. No use after delete, thank you. And that means, as a side effect, it is perfectly legal and right for you to assume that your caller is correct and isn't writing a race on you. And so if he's asking to destroy this object, it's because he knows he's done using it. If he's destroying it and not done using it, report the bug to the caller. So now we get to the two interesting functions. Find. Now let's look at find. Find is going to look for a certainty value. It's going to load the head object. By the way, head.load returns the raw pointer, so I can use auto. And it's also very nicely self-documenting. And then I'm simply going to go through the list. And remember, every node has an ordinary pointer. Yes, making sure I'm not lying. Every node has an ordinary pointer. And so I just walk through the list as usual, check does this node have the value I'm looking for? Are you my mommy? Are you my mommy? And finally, the answer is either yes, and I return a pointer to that element, which is a pointer into the actual element in the list, or I'm at the end and I return null. Everybody okay with that? We've all written this code single-threaded. We're sort of almost on the edges of our seat. Maybe we're a little on eggshells. Can it really be that easy concurrently? I thought this lock tree stuff was hard. Wait for it. Now let's look at push front. I will ask for microphones. So I'm happy to go back a slide if you've formed a question and then, because sometimes even just walking up, you go, oh yeah, I think I've got the answer. Now let's talk about push front. Here's what we want push front to do. So here's like the action diagram of here's what I want push front to do. I want to take the initial state, allocate a new node off to the side, link it to point as its next node, the current first node, and then swing the head pointer from its current first node to my new node. And we swing that head pointer by doing what? Exchange. OK, how many of you thought exchange? Good. All right. Here is a flawed, but single-threaded, I think it's correct single-threaded way to do this. We do a new node, we assign its t value, we assign next to head, p next to head, and then head equals p, so what's wrong with this code? It's erase, yes, and? Not durable, exactly. That assignment could lose updates, you could have two threads that are trying to insert at the same time, and if they do that, then you get into that middle state where there's a moment, a window, where they've both got their next pointers pointing to the same new head, and then they both set head. In this case, the last shall be first, because the last one wins and the first write gets clobbered. It's even funner if you under heavy, funner, that's probably not an English word. It's probably Canadian. I'm sorry. Actually, it's not. I am Canadian. I should not be making Canadian jokes. But it's OK, because we can talk about threads making progress. I think I've done that already, so I've given myself away. But it's even more fun if you have this lost update, and in that brief window of time, under heavy load, other threads are using the list, and different concurrent threads see the list in both states, one in one state, one in the other, and then they wake up and say, well, wait a minute, what do you mean that never happened? No, it was never true. But no, you didn't see that. And have a happy debugging session. So what we want to do instead is we want to call compare exchange, but we don't want to just call a single compare exchange, because remember we say if compare exchange expected to desired, we interpret that as am I the one who gets to change the atomic from expected to desired? The answer might be no, therefore you write a loop. And so we write the loop where we point to the current head, and then we say head compare exchange weak. Pro tip, always write weak if you're writing a loop, and write strong if you're not writing a loop. It's that easy. The reason is just weak on some architectures is allowed to fail spuriously, and that's OK if you're in a loop anyway, and it's more efficient most of the time. Weak is for loops, strong is for non-loops. So I'm going to try to compare exchange from p next, which is the expected value, the value of head that I just read, to me. If that succeeds, it means that head hasn't changed since I looked at it, which means nobody has inserted, and I'm OK, I'm done, and I drop out and I return. If it fails, remember there's this neat feature, thank you Lawrence Crowell. I've gone back and forth on whether I think this is a neat feature, but I think it's a neat feature. It actually updates pnext for you, because it knows that probably the next thing you're going to do is reread head. So I already know what the value was. It's not the one you expected, but I'm just going to tell you what it was and save you reading from it again. Actually handy here. So that compare exchange will also reload. It'll do the equivalent of that previous line, pnext equals head again, if it fails. And so you just keep on compare exchanging until you succeed. And you swing ahead from the value you expect to your node, and you're done. Easy cheesy? I'm curious, how many of you have actually written code like this in production? Most of the hands stayed up. Cool. Well, that was easy. So at least one person got me during the intermission. And in fact, I'm wearing his name badge. And you should swap name badges. It's kind of fun. And it said, but you're not showing the, I know, wait for it. That's the easy example. Now we're going to add one little function. How hard could it be? I'm now going to add pop. I mean, if you have push, you must have pop, right? How many of you have written singly linked list pop, a stack? It's easy, right? OK. Here we go, first cut. All I'm doing is adding this pop front function. And if you already know about the three-letter acronym problem, then don't raise your hand because you already know the answer, so don't spoil it for everybody else. But let's go and talk about pop front. Here's what we want it to do. The initial state is whatever. The intermediate state is we've swung the head pointer to the second node, which detaches the first node. It's no longer accessible by new people traversing and find. And then we delete that first node once it's been unlinked. How hard can it be? Here's some code. Look, let's just do what the documentation says. Somebody wrote the spec for the function. I've implemented it. Let's ship it. Load head if it's not null, then head equals p arrow next and delete p. Perfectly correct single-threaded code. What's wrong with it? Oh, there's so many things wrong with it. Anybody to start? You might delete next. Ah, Peter, yes?
Yeah. It races with finding.
It races with finding? In what way?
You might still hold the P and look for it after it's deleted.
So you're saying, oh, there might be a concurrent find that is, he's hopping the lily pads, he's hopping through the nodes on the list. He might have just started and he's on the first one and he's reading P next when you delete it out from under him. Yeah, that does seem unfriendly. Anything else?
It races with push too.
It races with push as well, yes. It races spectacularly with push. And of course, remember, for completeness, if find is already done and gone, what has it handed out? A raw pointer into the node. Now you could say it's the caller's responsibility to know that he deletes all pointers, but not all callers can do that. So there's problems for readers, there's problems for writers. What about concurrent inserts? What about concurrent erases, finds? It's funny that one of the hardest problems on this slide is delete p. Really is hard. Here's another attempt, still flawed, spoiler. I'm going to load head while compare exchange weak, because I'm now going to try to swing head from p to p next, so from its current value to next. If that succeeds, I know I'm not racing with inserters, say. What's wrong with that code? Same problem for readers. And if you're doing a concurrent find, he might be on that lily pad that you're now yanking out from under him because find is traversing. You might be on the first one still. And there's a subtle problem with writers. What if a concurrent writer is trying to insert? And now you get a beautiful dance called ABA. How many of you have heard of the ABA problem? Oh, wonderful. If there was any question as to whether we're in an advanced audience, that answers it. So let's talk about ABA. ABA basically means that the variable of any type, but in this case, this head pointer, has a certain value, and then you come back later, and it has the same value, but it's not the same value. Why? It's not the same object anymore. How could that be? If an int is 42 and I go away and I look and it's still 42, that must be okay. If it's a pointer, it might be pointing to a different object at the same location. How's that possible? Well, what if you deleted it and reallocated it? Such as if you start with this original state. Then step one of deletion is we're going to load head, so let's call that p like we had in the text. And then we have that expression p arrow next, and I'll assign that to a temporary just so I can talk about the name. And look, there it is. We've got that temporary variable pointing at the second element. So we've got first and second. So far, so good. Concurrently, we get another thread comes in and does 2 pops. Runs to completion in this window. Maybe we just got unlucky and got context switched at this inopportune time. Or if we're really unlucky, it might be 2 different threads, each doing a pop. We don't care. We're just as hosed. And he deletes 2 nodes. I'll delete 2 for fun because that means both pointers dangle. Double your money. Then someone else inserts a new node, and you know what? It's at the same memory location because it's on a free list. And allocators like to keep things hot in cache and reuse memory that you just deallocated of the same size because it was a node of t, right? So it says, oh, sure, I'll allocate one of those again for you. And now we're in this really awkward problem. The really awkward problem is that flashing arrow. Because that p is still pointing to an object at the same address of the same type, but it's not the same object. but he has no way of telling, because he has no idea that an object was destroyed, memory deallocated, reallocated, an object constructed again. It's not the same object. Address identity is not the same as object identity. And now what's he going to do? He's going to say, compare exchange from expected, which seems to be correct, to something new, which doesn't exist anymore. And now everything just blows up, and everybody has a bad day. Because not only is he pointing off into hyperspace, but nodes don't get deleted. The whole list is orphaned and floating away on the breeze. It's just horrible. At this point, I could easily consume a half an hour with ideas for how could we fix this, by not allowing the people who know about the ABA problem and thought about it for several years already to speak. Because people have got lots of PhDs and other things for doing work and trying to solve this problem in all sorts of ways. Here's just a sketch of how to deal with ABA problems. Option 1, use lazy garbage collection. That is a useful option for highly concurrent algorithms in this very narrow case. Option 2, in this case, use reference counting, which is also a form of garbage collection. This would mean atomic reference counting, more so than the usual atomicity in shared Putter. Option 3, make these pointers bigger, add a serial number to each pointer and increment the serial number every time you set the pointer. That works too, but now you require larger pointers, larger compare and swap operations. Then there's hazard pointers and a few other options you can use as well. And there are wonderfully advanced technical papers on how to do this. That's the ABA problem. Just the two deleters problem. But we still haven't even solved, even if we solve that with garbage collection or whatever, we still haven't solved the delete while traversing problem. Well, garbage collection actually would help with that. The idea that I'm popping something that somebody might still be sitting on, because I have no way to know with raw pointers alone, are they still sitting on it? Are they using that node? Lazy GC could help. Reference counting could help. One valid option would be never delete anything. Obviously, that doesn't scale, but in many situations, it's good enough. Something if deletions are rare, or if you can just batch them up until the whole data structure goes away, and it goes away soon enough so the memory spike isn't that important, and then you can clean them up. Region-based memory management uses this idea quite a bit, and it can be useful. You just logically delete it, you don't physically delete it. And then there are more esoteric options, like putting auxiliary nodes, and now you're getting more complicated and very researchy. For several years, I gave this example, and I never actually showed. I ended with those two slides, and it was a very disappointing way to end, because it was like, what do you mean? Yeah, well, here's some solutions. Go look at the literature. But how do I do this? Turns out C++11 actually lets you solve this problem. I have a deal for you. I'm going to talk about something that doesn't exist, but it almost exists. In fact, all of the examples I'm going to use on this slide, you can write in your production code today by changing the syntax just slightly. And I'll show you the cheat sheet at the end. You see where I write atomic of shared Putter of node? You can't actually write that in the C++ standard library. Some implementations allow it, but they do the wrong thing. Do not try that. For convenience, because we've been talking about atomics, I'm going to show what the operations would be, the normal atomic operations if you could have an atomic of shared Putter. It's not a pod, that's why you can't have it, but atomic of shared Putter, because all the operations we care about exist in the standard today as non-member functions. They're just free functions, there's no atomic of. And I'm currently working on a proposal that we talked about last Thursday here in town at the ISO concurrency and parallelism meeting that was co-located with CppCon, and looks like there's some interest in pursuing the proposal I'm making, so I'll come up with a new paper for November. Because I would like actually atomic of unique Putter and atomic of weak Putter as well, but let's just talk about atomic of shared Putter. All of the code I'm going to show you again, you can't type it exactly as it is, but I'll show you the cheat sheet where you can write this today in a conforming C++11 implementation library and use the same features. Just as you can't say atomic of shared Putter, so when you read from one, you have to remember to call the non-member load function, for example. But all the functions are there. You can do this. I'll show the simple syntax. The head is now going to be an atomic reference counted smart pointer, an atomic shared Putter to the node. That means while nobody's using the list, head is the only pointer to it, refs is 1 on that first node. Each node contains a regular shared pointer to the next node. Again, I'm going to, as Peter said, simply not write, but except I'll explicitly point out that the defaults work for the constructor and the destructor for slist. Notice I don't actually have to write that cleanup loop anymore, because that's so C, right? It's like, so C++98, that I have to write that cleanup while we take the first node, delete it. Like, delete? We don't write delete anymore. Really? Like, don't write delete anymore. Use shared putter. Well, that means we can just use the automatic destructor. And now I'm going to have this class reference. Instead of returning a raw pointer from find, I'm going to return a reference to the found element if I found one. So the way I'm going to do it is this. And notice I'm using C++14 auto return type deduction, because why not? And compilers support this now. If your compiler doesn't yet, it will in a few months. And if you're on the major compilers, I'm going to load head. So I'm going to load that shared putter. At the end of that line, I have a second shared putter. So now refs is 2, assuming nothing else is going on. Refs is now 2. Head's got 1. I've got 1. While P and P arrow T isn't the thing I'm looking for, I'll keep going through the list. And finally, either I'll fall off the end or I'll find it. Either way, I'm going to return a reference to the shared putter, which is either non-null if I found something or null if I found something. It's a shared putter to a node. Now, we can see why this is safer than returning a raw pointer, right? I know that I'm not going to dangle because why? How do you think class reference is implemented? How would you implement class reference? A pointer and what kind? You're on the right track. Who said that? Shared pointer of node. Right. In fact, that's its only data member. Here's the code. That should work. I compiled it, ship it. And so you construct a reference from a shared pointer. And all it does is it provides the dereference operators. It's kind of like an iterator, but I just call it reference because it's only in one place. Stefan, you can tell me later.
There's a sneakier way to implement this.
You can tell me later because we want to show people how to do it, not get too detailed. So please.
Yeah. Shared putter's aliasing constructor.
So write for clarity and correctness first, people. This code is simple enough. And when we dereference, we return a reference to the T. When we say arrow, we return a pointer to the T. So this reference is like a proxy for that T. But because it keeps a shared putter to the node, it's not going to keep that node alive. For as long as even the caller I handed it out to, who I have no idea who he is or how long he keeps the reference, that's OK, because I've now made that type and memory safe. Question?
This kind of destructor, will it not blow the stack? It's like recursion, right?
This kind of destructor is it recursive? Possibly. Yeah. I'd have to think about it.
So it will blow the stack if the list is long enough.
Yeah, it's just shared putters. But that's an interesting point. I'll think about that. Because the shared putter destructor will destroy the shared putter, which we'll call the object, yes. But it's automatic. One more.
The older version of find, when it wasn't in the list, would return a null pointer. What happens now when you're looking for something and it's not in the list?
Excellent question. What happens? You get an empty reference. So you get a reference that's constructed from null, because if you see the while loop there, it'll terminate if we find something or if P is null. In the case that P is null, we fall through the end. I'm still going to return reference constructed from move of P. And you don't need to write that move for correctness, but why bump and then decrement the reference count? You don't want to do that just for nothing. So I move P, and I could be moving a null pointer. And that way, so reference could be null, which means that we should provide some way, such as you can test the error. We should probably provide an implicit test for whether the reference is null or not. That would be a good thing to do.
Herb,
Yeah, change the word then. OK, one more, but only because you're Peter, and that's my middle name.
Thank you. Why couldn't have you used a shared putter node in the first place instead of reference?
I could have. I'm fixing another problem while I'm at it. So the first version is what you routinely see people who are writing lock-free code do. And they hand out pointers, and it's up to the caller to make sure about lifetimes and such. Let's make the ABA problem go away and solve the main problem while also making the world safe for our users. Good question. So here is now a class reference. Now, I still haven't shown you what two important functions. I still haven't shown you the insert and the pop. So let's look at push front. Push front says, well, I need a new node, so I'm going to make shared new node. And I'm going to set its t-value. I'm going to set its next pointer to head. And I don't need to write .load there because I already get that conversion. And now I'm going to try to swing head to point from the current first node to my new node. And again, as usual, I loop if it doesn't work the first time. So I compare exchange until I get to swing head to my new node that's correctly linked into what then was the current node. If there's contention, that will work. And now the one that was hard before, pop front, is actually implementable in a couple of lines. I load head, and then I try to, as long as it's not null, I try to swing head from P to P arrow next. One of these days I'm going to succeed, and I'm done. I want you to think about this. Look at the slides later, because it is not obvious at a 30-second reading that that actually is correct. I think it is really cool that if you notice you have the atomic shared pointer operations in the library, a previously very difficult problem that you had to tell people resort to garbage collection, resort to hazard pointers, or weird esoterica like that, you can actually write in normal code, and it's correct if you have atomic shared putter. Now, we don't have atomic shared putter as a type, but we have the equivalent functions. So you can, in fact, write this today if your standard library implements those functions. Now, one question. Well, so atomic of shared putter won't compile with GCC today, but hopefully they've implemented the non-member functions I'm going to show you on the next slide. So just wait for one more slide. Where is the delete here, by the way? Notice we say pop front, but we used to say delete a node. Shared pointer. OK, so the shared pointer, right. Where is the delete? Which shared pointer? Are you sure? Yes, it's the last one. So it might be P, but if nobody else is looking at it, wonderful, snazzy, everything's groovy. Yeah, that's still pretty current. But if somebody else was looking at it, that delete might be in the reference, which is great. Now or in the concurrent find, which is also safe. The find thread might be the one to actually delete the node if it was just hopping over it. Now, let me just actually make a aside about this. How many of you have heard of this deliciously wonderful concept? It's got a complicated word, but it's really delicious and wonderful, called linearizability. Have any of you heard of linearizability? Oh, very few. I see like 3 hands. 4 hands. OK, so linearizability, especially for concurrent code like this. It is the property that you get this, even though some functions can overlap, like a find could overlap with an insert being done on another thread, even if they overlap, you get the same semantics as if you had executed them non-overlapped. Whichever one started first, the guy who came in second, however they start, is going to see the world in the same state as if he had waited for the first one to complete get out, as you would have with a mutex, say, where only one can run at a time, except you get better concurrency, but you still get the same one-at-a-time semantics you would get with lockstep use of mutexes, one-at-a-time use of mutexes. But you can overlap. That can be really efficient. It's good for scalability that you can overlap, but that you can reason about it as if one had gone before the other is really cool. And here we have code where we can reason about that even though they overlap, it's as if one ran first. Because, for example, the find, if we have a find and a pop front happening at the same time, let's say the find starts a little earlier, so he sees that old node that we're about to pop. While he's still sitting on it, we reach in there and we pop front. Well, we don't delete the node because he's still got a reference to it. We detach head's reference to it, and now head points to the second node. That means any new find will see the list in the new state. But because this first find started before my pop, he continues to traverse the list and see it as in the same state it was when he entered, even though the pop front has been able to be partly concurrent with him. And as a side effect, he just happens to be the one to delete the node when he leaves. But that's an implementation detail. So it's linearizable, it's concurrent, but it's as if one ran completely before the other. That's a concept worth getting to know. That's a really important concept because it helps us to make sure that when we do all this abstruse stuff that's really complicated and subtle, as long as we can still reduce it to one thing happened before the other, it's the same as if, then we know we're still in a sane world. When you start getting beyond that, when you can't prove something is linearizable, be very suspicious whether it's correct or not. Because it is very easy to fool yourself, fool myself, into thinking code is correct. That, yeah, I think it'll be good. Yeah, well, it's either linearizable or it isn't. If it's not, suddenly the bar got a lot higher to prove that it's correct. So having said that now, let's actually analyze this to try to prove to ourselves a little bit that this is true, that this is safe. Let's say I have a concurrent pop and pop. That was one of the problems before. So they're both going to load the head, say, and they're both going to try to swing the head from the value they just read to the second value. Well, remember, compare exchange means, am I the one who got to swing the value from expected to desired, from the first value to the second value? If both of them load the same value for head, and they both compare exchange weak, one will happen first. I don't know which one, but one of them will happen first. It will succeed, it will swing it, and the second one will say, darn, let me try again. So we have two concurrent pops work correctly. One of those two is going to succeed, the other one's going to spin, and ABA can't happen in this case because there's no delete as long as anybody has a pointer to the node, and so there's no memory recycling, which is kind of nice. So now let's look at insert and pop. Well, if I have a push front and a pop, one is creating a new node, trying to stuff it, it's loading the current head into its next pointer, and then it tries to swing head from its next pointer to its new node, while somebody else is trying to swing head from the first node to the second node already in the list. Well, one of those two is going to succeed. That's the only point of interference. One of them is going to succeed, one of them is going to retry. Perfectly fine. Any questions about why this is safe? It's kind of neat that simple code is correct. Like, I thought we gave that up with atomics, but you know what? Maybe not. Finally, find and pop. We described this one already. Again, here there's only one compare exchange. The other one is just loading the head node. And thanks to reference counting, find keeps its node and its successors alive. So even if in the future we add more kinds of options for deleting nodes, say delete the first two nodes in the list, find as soon as he started will still see the list in the same state that he saw it originally, because keeping the first node alive is good enough to keep the whole list alive, including that chain of nodes that somebody else might be trimming, which is kind of cool. And there's that important concept of linearizability. We should try to find shorter words. Linearizability. 8 syllables and such a, that's pretty good for that letter count. We can do better, but good thing to know about. So let's look at what find and pop does now. So let's say I've got a find that's on one of these nodes, and 2 pops complete. I've done the find. Then another thread does pop and then pop again. So notice now head is pointing at what was the third node, but find is still OK. He's pointing at the second node, and he's still traversing the list as it was, in the state that it was when he first entered the system, when he first entered the concurrent data structure. So here's the translation guide. You can't write the exact text I wrote on the previous slides, but here is the translation guide that you can write in a conforming C++11 implementation. You can't write atomic of shared putter, so just write shared putter. And remember, comment. I really want this to be atomic. Please don't forget to call the atomic instructions every time you access this. Anytime you say a.load in my slides, write the non-member atomic load address of A. That's the same, that's the equivalent. A.compare exchange weak ED becomes atomic compare exchange weak address of A, address of E, D. These are equivalent, they will work. It turns out the reason I am pushing for the standard to include the left-hand side and the atomic versions, atomic angle versions, or similar as synonyms, there's 2 problems with the right-hand side, which exists today, it works, but there's 2 problems with it. First, you can be more efficient if you write the left-hand side for implementation reasons. Second, Usability, the right-hand side, you have today, but you do have to remember every time you touch that shared putter, use that atomic load function to read it. Use the atomic compare exchange weak. Use the atomic store function to write to it. If you forget and you just read from your shared putter, your code will compile and appear to work. You just wrote a race. And the definition of what or how a race manifests nearly always is your code compiles and appears to work. And so it makes it more brittle to use. If you say atomic on the type, on the variable, you say it once when you declare the variable, and all your operations are correct. You can't forget the atomicity. You can still write bugs, of course, but it's just the usual bugs. The atomic operations are correct. You don't need to remember every time you touch the variable to write the right function. What I would suggest you do in the meantime is to write your own atomic underscore shared underscore putter wrapper that it simply defers to all the non-member functions in the standard. And then you will have something very usable and useful. And what you do internally is just have an atomic bool or something, just have a spin lock for now. That's the simplest thing to do to acquire access to it when you copy it in or out. That's something that actually with the tools we've talked about today, you should be able to write. Question here.
I'm not admittedly familiar with the implementation of shared putter, but doesn't this sort of assume that it's going to basically lose your order 1 access at the front pop and push because it has to increment the reference of every single node down the line?
It is an open question, including at the standards meeting on Thursday, whether atomic shared putter can be written to be lock-free. We believe, at least I believe, even if the answer is no, that it's still useful. And it can still give you better performance in many cases, and certainly better correctness than the raw pointer, and better performance than using a mutex in some cases. I was given an action item on Thursday between now and November to go try to put together a benchmark that actually shows it could be competitive or better to actually justify that. So that's one reason. I forgot the second part of your question.
So no.
Oh yes, because
maybe I didn't explain
you can make it
correctly.
lock-free. Even if you can't make it lock-free, it may be that you can still do better. Certainly, if you make it lock-free, now it becomes possible to write lock-free data structures that we can't write in portable code today.
No, I guess my question was, maybe I didn't explain it correctly, but does like acquiring a copy of one of these nodes require you to increment like a so-called reference count on every single one of the successor nodes?
Well,
So do we no longer have the like guarantees of
No.
a? Okay.
yes, it is bad. It is bad enough, and the worst part of this, which hopefully won't be bad, we'll find out, is that as you traverse, you have to take a reference count on each node while you're on it, and then you let go of it. But you only do it on each node you're sitting on. The node itself already holds a reference on the next node, so you don't need to do anything special. So if you hold a reference, if you hold an addref, sorry, comm speak, it's the people I hang around with. If you increment your reference count on this node, it's as good as keeping alive. You've got a reference count basically on the rest of the list from that point on because they own the next thing.
Oh, thank you.
Fedor?
With regard to you can do it today, so if I do it today, I will be incrementing and decrementing reference counts inside the shared putter. Is that atomic?
So if you implement it as I described today, certainly if you use these free functions, and the only purpose of those is to read and to write and compare exchange shared putters themselves,
Yes.
you'll be fine.
Shared putter is the same size as a normal putter, right?
Not necessarily.
Well, okay, so where is the reference count?
Oh, the reference count is wherever it is in shared putter.
So there is an increment.
Yeah.
I don't see
copy,
I don't see atomic increment
Ah,
here.
if you see atomic load of address of A, so that is giving you a copy. That function exists today on the right-hand side. Atomic load of %A, where A is a shared putter. If you do that, it returns you a shared putter, a copy of the one that's inside.
And somewhere there has
Which
to be
means,
a reference count.
but it's just a copy of the one inside. That's just the usual bump the reference count, whatever copying it usually does. The only reason you need to call the special atomic load function is it'll take a spin lock on that particular shared putter to make sure that it doesn't get torn if somebody else is reading and writing that particular shared putter while you're taking the copy. But internally, it's just the same as taking a copy of any shared putter. It always bumps the
Sure,
under the covers
but
reference count.
let's say two threads are doing 2 atomic loads at the same time.
Well, first of all, one will go before the other, right?
Well, okay, they'll do the copying.
No, one will happen before the other. But it's
what
but
guarantees that?
the question. So if the question is the increment of the reference count inside the shared putter itself atomic? It's always atomic anyway. And there's nothing special about that because it's already atomic under the covers in normal shared putter use, because you don't know if copying the shared putter, this const operation on a shared putter, reading it could have the side effect. That's already true under the covers. All you need to do to think about atomic load is, it's a way of safely, if I've got to look at that shared putter sitting there, I can have 2 threads, take a copy of it, and know that that's safe. But they'll do exactly the same as they normally would do to take a copy. They'll bump the shared ref count, which is atomic under the covers already. But all atomic load is doing is to make sure those 2 things don't happen at the same time. One happens before the other. That's all that's for.
Which means that it will actually have to take a lock.
Yeah, that's why I said if you implement this yourself, one easy way to do it is in your, if you have atomic underscore shared underscore putter, is to have a shared putter and an atomic flag.
No,
Atomic
I mean
rule.
this thing, as written today, this atomic underscore load will have to take a lock.
There are various ways to implement it. And using look-aside tables, but you're right, they need additional information. They need a lock of some sort.
Because the state is more complex than a single atomic word.
I get to finish answering the question too. So it takes a lock for a specific shared putter or for a group of shared putters on a page or some other way you can implement those free functions various ways. They are all correct. If you want more, ask me afterwards. They are correct. You can be more efficient if you do it the left-hand way, because I can just put a flag inside every atomic shared putter, which is the way I recommend people wrap it today. And furthermore, more importantly to me, the code on the left is more correct, because you just say atomic on my shared putter, and you don't have to remember on every use of the atomic to make sure you say the right incantation. So come up afterwards if that didn't answer your question. But it is safe. You just have to use the free functions for now.
At least one implementation of shared pointer I'm familiar with has a mutex lock built into the shared pointer for the reference count, the boost one at least on Solaris. So you may not get a lockless thing anyway because the shared pointer itself may have a lock.
And any synchronization inside the shared putter that would be there anyway has to be there anyway, and implementations can compete on efficiency.
Do you know if there are implementations of shared pointer that use atomic?
Yes.
There are.
Yeah.
The GCC, yeah.
Everybody does or should.
Yeah, well, not unfortunately on Solaris with that.
So it sounds like we understand that if shared putter does the right thing, here are the functions to call. Over a beer, we can talk about the implementation details of shared putter itself on various systems today. Assume you've got a correct shared putter. Here's how you use it atomically. Now, having said that, let's see how we're doing. 358. We're right on the edge. For more information, see all these wonderful papers. All sorts of papers. Some of them researchy. Some got people with PhDs or at least some advanced degrees. Questions. Oh, but wait, we have time for bonus slides. Now we'll see if my estimate for 30 slides is accurate. Because I wrote this in an article for Dr. Jobs, one of the effective concurrency articles a few years ago. And I never wrote about it again since. I have never shown these slides in a course. And I really want to show them. So this is material that you will find in print in exactly one place that I've never presented otherwise. But I just wanted to put them in for CppCon. Here is essentially code somebody else wrote. So I took existing published code, I believe it was in Dr. Dobbs itself for an earlier issue, for a baseline low lock queue. And this is after I fixed it because it had some concurrency problems. But here is basically a design that's not bad. But it's a nice optimization example because we'll see how we can incrementally make it even better by doing what? Measuring. All together now, by doing what? Measuring. How many of you know who Howard Hinnant is? Is Howard in this room? Yell if you are. Okay, somewhere in the building. I hope he's giving a talk. He is basically the implementer of Clang's standard library, the standard library that ships with Clang. He was essentially the only developer, or only one of two, until about a year ago. So he knows his stuff, and he's been in the committee for a long time. He was a library working group chair. Great guy. I was having a conversation with him just about a week ago in email. And a couple of us were having a conversation that you'll hear more about on Friday. And one of the people on the thread responded to something Howard had said with, but I know that's efficient and that's not going to be a problem, or something to that effect. And Howard, who has the qualifications I just described, said, and I believe this is an exact quote, "I find myself increasingly unqualified to make any performance statements without measuring." Let's look at this baseline code and measure. So this low lock queue, it's not entirely lock-free, so I'll just call it a low lock queue. It has a node which contains a value and an atomic next pointer, because we're going to do something a bit different with it. So similar but different. It's going to have an atomic next pointer. And I have the 5 accessory variables at the bottom. We'll get that down to 4 later, but there's 5 accessory variables. Node pointer first, a node pointer last, a divider node. Now, what the divider is, he points to a boundary between the producers and the consumers. So that the consumers are consuming on one part and the producers are producing on another part. And it makes a nice boundary for them so they don't overlap and overrun each other. And then I'm going to have this atomic flag, this atomic bool that I just mentioned. You put one of those inside your atomic shared putter that you're going to wrap yourself tonight, called a producer lock and a consumer lock. And I'm not going to lie, I'm going to call them a lock, because you know what? We're going to implement a spin lock. We're just going to spin until we turn it to true, and that's fine. Spin locks are great under low contention, by the way. And we had this discussion during the break. A lot of mutexes are implemented. There's hundreds of strategies, but a lot of mutexes are implemented to first spin a little before yielding your thread, because maybe you'll get lucky. And if you often get it, why not do that? But we could easily consume the rest of the talk talking about our favorite mutex implementation. We're just going to spin here. The constructor does the following. The constructor creates one node. The initial state is first, last, and divider all point to the same node. One happy family. And we set the producer and consumer locks to false. The destructor is very similar to what we just saw. It just runs through the list and deletes the nodes. Consume. We have produce and consume. Only 2 functions. The consumer first gets exclusive access to the consumption part. So we're only going to allow one consumer to be consuming at a time. We're going to allow concurrent producer with consumer, but only one consumer at a time in the critical section. The consumer first says, let me make sure I'm the only consumer. The way I do that is I spin in a while loop on exchange true. I'm going to write the value true to the lock variable, and it's going to return me the old value. If the old value was true, well, I redundantly set it to true and somebody already had it, so I'll spin again. But if the old value was false, then I got to be the one to change it from false to true. You'll see this idiom a lot. While exchange true, semicolon. I try to make it a little less hard to read by saying while exchange true, brace, brace. If you want to be even more explicit, you could say while exchange true, brace, semicolon, brace. Once I have the exclusivity, then I can do what I want in the consumer part of the data structure. In particular, I'm now going to say, is the divider's next pointer null? If so, there's nothing to consume. But if it's not null, the queue is not empty, and I'm now going to read that divider arrow next node's value. I'm going to read it out. Then I'm going to move divider to its next node, and I'm going to release my lock. And return true. Otherwise, if it wasn't empty, I'll release the lock and return false. And so here are the critical sections. One of the key things you might notice if you're paying close attention to what's going on is I'm copying the t value inside the critical section. We'll come back to that. Any questions about the basic meaning of this code and how it works? OK. Well, that's half of it. Now it's just the producer. So let's look at the producer. The producer is going to put things into the producer's part of the data structure. Again, only one producer at a time. So again, we see this while exchange true spin. But I'm going to wait for the producer lock. So once I know I'm in there, I'm the only producer, then I'm going to take the last pointer. The last pointer. I've already created a new node, by the way, because I'm producing something. I'm going to take the last pointer and have it point to my new node. Then so I'm pretty much done at this point, and I'm going to set last to that new node as well. But I'm going to do a little more work, because so far I haven't showed you how we clean up consumed objects. You might have noticed on the previous slide that we don't delete anything. We just consume and then walk past it. Well, in this model, which is the way the code was originally written, so I left it this way, the producer then does this while loop where he does cleanup of any consumed node since the last time a producer ran. So the producer will then lazily clean up anything that's been consumed since the last producer. So you won't ever get too much cruft up there. As long as a producer runs once in a while, it'll clean things up. Then we release the lock and return true, because we always succeed in producing in this model. Any questions about the basic meaning of that code? So now let's see how fast it is. Here are key things to look for. We talked about throughput. That is, how many, in this case, how many T's can I shove through that queue per unit time? Produce it, consume it. What's my throughput? Number of T's I can shove through the queue. What's my scalability? How many cores can I scale to where I use more cores, more threads, more producers and consumers? Because now this is multi-producer, multi-consumer now, right? Unbounded. How much can I scale to make use of the larger and larger numbers of producers and consumers before my lowly queue becomes a bottleneck? The things that affect this, two things in particular we're going to analyze: contention and oversubscription. Contention is how much do threads interfere with each other, and we're going to analyze both producers and consumers. And oversubscription, what if I have more threads, more active threads than hardware resources or cores? So here are some measurements. The way I did these measurements is on the vertical axis, you've got the number of consumer threads, which go from 1 to 24. And on the horizontal axis, the number of producer threads. And we're going to keep that consistent throughout. The size of the circle at each combination of number of producers, number of consumers, is the throughput, the number of nodes that I can shove through. And I've just arbitrarily scaled it to the biggest one, like you can see down in the lower left corner at 2 producers, 1 consumer. That's just arbitrarily, that size is the biggest of all the values, and then the others are scaled appropriately. And so you need to look at the legend at the bottom to see what that maximum is. So on the left-hand side, I'm using what I'm calling smaller objects. They basically just contain 10 strings. So I'm copying 10 strings. And that's the object, like a widget with an array of 10 strings, for example. That's the object I'm shoving through the queue. That's my T that I'm putting in each node. And on the right-hand side, it's an object with 100 strings. So a big fat object, which is a proxy for something with lots of state, whether it's strings or an object graph or who knows what. You'll notice that the maximum throughput on the left-hand side for small objects is, the maximum is 88,000 objects per second. This is normalized per second. On the right-hand side, I'm getting only about 11,300 as a max for larger objects. And there's a few interesting things here. The scalability, how good's the scalability here? Not very good. So I reach my maximum where? About 2 producers, 1 consumer, roughly in both cases. I get a little lucky at 4 producers, 1 consumer on the right-hand side. But my maximum scalability is at 3 threads, and it goes downhill from there. Not only do I get less throughput, but using more threads causes less work to be done.
How many cores are you running on?
That's an excellent question. You probably saw my notes. How many cores am I running on? You should be able to read it off the slide. I heard a number? 24. How did you intuit 24? You see the diagonal line. So tell me about this diagonal. What is the diagonal line here? So if you look closely, especially at the right-hand side, and this is subtle, I kind of said, well, you should be able to read it off. Well, only if you know what to look for. So I'm very glad that question was asked, wherever it was asked, because that's exactly the next line I was going to draw. This is a 24-core system. You can read it off, not the left-hand graph, it's not visible there, but you can read it off the right-hand graph, because there you can see the oversubscription cliff. Especially when you get larger number of producers, you fall off a cliff of throughput as soon as you pass number of producers plus number of consumers is more than 24. And it turns out that if you look at going up, that oversubscribing, but with more consumers, is less bad. So it's interesting. That immediately tells you there's contention and thrashing and that kind of thing, and it's worse for producers than consumers. But yes, you caught me out. This is a 24-core system. So that was excellent. And any other points to make on this? Yeah, adding more threads just doesn't get more objects through the queue after you go beyond 3 threads, which is kind of unsatisfying. So remember those numbers. I'll show this again, but 88,000 and 11,000. We're going to take 3 successive steps to improve this. The first is to shrink the consumer critical section. And for better performance, we're going to do more heap allocation. Exactly. That is why I wrote wait, what on the slide, and I got what audibly from the audience. So I'll count that as 50% success. Well, sometimes it's good to allocate from the heap. You just need to be conscious of when you do it. Sharp tool, right? So the reason is because if the T object is physically in the node, it's tied to the node, it turns out that in the previous code, that was a reason why we had to do the copying of the object inside the critical section, because we need still access to that node. If we move it outside the node, so every node contains a pointer to a separately allocated T, at first you think, oh my goodness, I'm tearing my balding hairs out because that's double the number of memory allocations. Yes, that's a cost. But I get it back and more in that I can shrink that critical section and move work outside of the critical section so other threads can make more progress. I'm slower, but I'm making lots of other people faster. And that's a very nice trade-off to think about. So here are the diffs. On this slide and the next are the diffs from the previous example. My node, again, is holding a pointer, a T star, instead of a T by value, initialize null. And here is the only difference really is on, the main difference is on consume here. And in particular, what I'm going to do is move the copying of that dequeued object and the deletion of the value outside the critical section. So what we're going to do here, should I explain the code first, or is the question on the previous slide?
From the previous slide, and partly because of this, can you just, instead of copying and allocating in memory, just do a move?
Could you do a move? That's still going to be work,
Yeah.
but you're going to be doing, well, it's not necessarily less
Well,
work.
for strings, it would be significantly less, right?
We'll talk more about that on Friday, about the costs of moves. And strings in particular, you'll love the strings. Wait for it. So now you have something to look forward to all week. Yes. But so there are other things you could do. I want to move all the cost of copying out. Gee whiz. So, and the destruction of the T and so forth. So now let's take a look at this. Where were we? Yes, so here's the consumer. I'll still take my compare exchange lock, but now if divider next doesn't equal null like before, now I'm going to take a pointer to the value out of the divider, set the pointer actually in the list to null, and immediately fix up divider, immediately release my critical section, and then below that, copy result equals star value and delete value. So I'm doing more work. I'm doing an allocation on entry, and here I'm showing the deallocation and deletion, but it's outside that critical section. That is the only change. Do you think it'll make a difference? Let me rephrase. How much of a difference do you think that will make? Huge. Must be huge, otherwise it wouldn't be worth talking about. Well, not necessarily, because I would be very happy sometimes with a 5% or a 20% performance improvement. Do we have any guesses? For those who haven't Googled my previous article and are looking at the slides right now, pick a number. Do I have 10% faster? 100% faster. So 2x. OK, I'm into 2x. Do I have 3x? Do I have 10x? Do I have 100x? Because you may believe anything, so why not try? See, I'd be happy with like 20%. I didn't know, so I measured. By the way, next question is, for which case? Right? That's why I didn't show all possible cases, but I showed at least 2 because it's not always the same. So let's take a look. Here was the previous slide. Here is the new slide. Let's go back and forth. So first of all, as I go back and forth, notice that the throughput in both cases, the throughput on the right-hand side is about 10x, maximum throughput, and I get it at much higher numbers of producers and consumers. So what that tells me is I have improved the right-hand side by enabling more scalability, by reducing thread contention so I can actually make use of more. I'm not going to get that throughput with smaller numbers of threads, but now I can scale to larger numbers. And in fact, I start to actually make it all the way, on the right-hand side at least, I make it all the way to the oversubscription wall, where I'm oversubscribing the machine with more threads, active threads than there are cores, and still not doing too bad as long as I don't add too many more consumers, which is a much better picture compared to here. So remember, a bubble here is not the same as a bubble here, because here the max bubble on the right-hand side is 111,000. Here it's 11,000. But now let's look at the left-hand side. It's gone from 88 to 269, so another, what, 3.5x performance improvement. And I'm getting somewhat more scalability even for small objects, which is kind of nice. I'm now scaling up to, maybe 7,5 or something like that. You can sort of roughly read it off. But then I'm starting to lose scalability again because there's contention and interference, where beyond that I'm using, in both directions, I'm using more threads and more cores, but getting less actual work done. I'm spending more time spinning and waiting, and those kinds of things. So that's interesting. What do you think? Worth it? Pretty good? Check it in? I mean, definitely check it in once you've tested it, because this is worth it, but shall we go for more? I think we should go for more. Let's reduce contention on the head. In the previous two examples, notice that the producer lazily cleaned up the consumed nodes. That's a perfectly valid design, but just think about it. It means that the producer inserts nodes at one end, consumers consume at the other end, and producers clean up at that same end. So now you've got producers and consumers both doing work at the consume end of the queue, one to consume stuff and one to clean up. So they're touching the same memory. There's going to be some contention there. Maybe we should divide those responsibilities more. And in particular, let's let each consumer trim its node as it deletes it. That might have seemed like something you would want to do anyway, so let's actually try that. As a bonus, we don't need divider anymore, it turns out, in this system. So here's the main difference. So the constructor is the same, except we removed the assignment to divider. It doesn't exist anymore. On the consume side, we are now going to spin until we get access. Then we're going to do those green lines. We're going to go through and remember the old first node as we move along and consume something. And then outside the critical section, we delete the old first node. So one of the nice things is, first, it's the consumer who's doing the cleanup of stuff he was already touching anyway, which is nice and hot for cache. But second, he's doing it outside the critical section, whereas before, the producer, if I remember right, was doing it inside the critical section. And that's the main change for the consumer. The producer is a lot simpler. In fact, I can't really show you the green diffs because it's strikeouts. It's like I've just removed code, which I've moved into the consumer. The producer is now making a new node, getting exclusivity, and he's just doing a few pointer assignments and then letting go exclusivity. Question here.
Yeah, in the previous example, when you moved the heap allocations outside of the critical section, how badly what price did you have to pay in the low multi-threading numbers? Obviously, you got scalability, but did you pay a price if you had fewer cores?
You can take a look at the graphs to read it off. I believe there wasn't too much of a penalty, and certainly you make it up for when you get scalability. Now again, this is an example of don't optimize prematurely. Don't make an optimization that is going to blossom for scalability when you have 200 cores if you're never going to have more than, say, 4. Now you've got this wonderful system that's never going to get exercised, and maybe you've got some penalties in the meantime. As long as I'm actually going to go past a handful or 2 handfuls of active threads, I know without looking at how much it's pessimized at lower numbers that it was worth it, because I know I'm getting overall higher throughput than would have been possible before. But that's an excellent trade-off question.
Thank you.
Is the question about this example?
Previous one.
OK. One more question about the previous example, because I have one more to show you. Go ahead.
My question is, when you do memory allocation, you also do some locking. The allocator is what
I used whatever memory allocator happened to be there. Don't know if it took a lock.
But you can kind of can use your own locking by, say, creating circle buffer, and
you can write your own memory allocator as well. That's true.
Yeah, so that
Yes. So you could further do optimizations on things like the memory allocator to maybe further improve the first one. In fact, that can be done with all of these, because examples 2, 3, and 4 oh, I've given away how many examples there are all going to all use the T on the heap, so you can, in addition to everything I'm showing, further optimize allocation, for example. But now, looking at what we just did here, we just moved responsibility for cleanup to the consumer, who was touching that memory anyway. Clean up nodes as you go, right? Good hygiene, nice and orderly. Put your toys away after you're done playing with them, that kind of thing. And we've reduced the divider data member. How much do you think that will help? Don't have too high expectations. Let's see. Here's what we had. And we go from 269 in the left case to 486, a nice computing number on Intel platforms. And we get better scalability. We're now at least approaching the line. We still aren't fully maxing out the system, but at least we can start to see the oversubscription line. And we go from 111 to about 115, and about the same on the right-hand side. So now that optimization helped, especially when the work was dominated by the queue operations, not by the other copying and stuff we were doing. And here's the fourth and final example. I'm going to leave the code the same. I'm going to leave it structurally the same. I'm going to leave the data the same, except I'm going to add only one thing, and that is alignment. The only thing I'm going to do is force that certain variables, that each node and each of those pointers, 4 pointers at the bottom, are on its own cache line. The way I can do that today in C++ was with align as, hooray, hooray. Unfortunately, align as is standard, cache line size is not. Go find your own. Conservatively, 128 should be plenty on every main modern system I know of. Some are 32, 64, 128. If you make just this change, you go from this, 486 and 115, to 583 and 114. So not much improvement on the large objects where we're dominated by the cost of copying and other work. But we're getting better throughput for small objects and even passing the oversubscription line. We're not being as penalized when we pass more than 24 active threads. We are still somewhat, but we're actually, by reducing contention, that memory pressure in the memory manager to deal with false sharing, we've removed a piece of contention and we can see it in our scalability. As our last thing, take this line of 2 producers for every 1 consumer and analyze the 4 examples' performance across that line, because that sort of seems to be the sweet spot that they all scale pretty well at. For small, here are examples 1 through 4, unsurprisingly from bottom to top. Number 4 gets the best scalability. Not only do they go higher, but they go further and go higher. They get higher at further points, which tells you about their scalability. By the way, this graph will help answer the previous question about was there a penalty for if you have lower numbers. Doesn't look like it, not very much, at least not for that line. And if you look at the right-hand side, this is still for small strings. Another way to look at this is basically invert it and figure out what percentage of total throughput, what your relative scaling factor is. And you can see that we're doing better with each of those modifications, including that last one. Just adding alignment took us from the green line to the purple line, which was pretty good. For large objects, there's less of a difference. But you can still see some benefit. And it looks like the main benefit we got was simply from taking that T out of the node and putting it in its own separate heap allocation. So sometimes that's good. Don't go out and tell everybody that, oh, look, it's better to separately allocate things, because that's awful most of the time. Here, because it helped us get a different effect in independence, sometimes an extra indirection is the solution, the correct solution to a computing problem. In this case, it was a legitimate thing to do. I have to finish with a rant, and that is, do you notice these wonderful Excel auto-fitted curves? Now, don't blame Excel. All auto-generated curves do this, even if you calculated the formula yourself. They're very helpful, right? They can sort of let us see what's happening. In this particular case, they actually obscure things. Are those the same curves you would have drawn if they weren't there? Like, take a look at if the curves weren't there, are those the same curves you would have drawn? No, because they actually obscure. They made it look so nice and smooth. It's like a party slide. Yeah, if I drew these myself, I would have noticed there's a cliff. There's a discontinuity where I leave a region of predictable and fairly rising performance where suddenly there's a discontinuity where not only do I go off a performance cliff, but I get extreme variability, because those numbers start to jitter all over the place when I pass that over subscription boundary. Just a reminder not to rely too much on your automatically generated curves. Look at the data yourself. They're not a substitute for when you measure, to look at the data and see what's really there. Doing it this way, writing the curves ourselves, we can really see the cost of oversubscription, both in performance and in variability and unpredictability. So what have we learned? To improve scalability, minimize contention, make critical sections smaller. Isolate threads to use different parts of the data structure instead of both mucking around in the same part, if you can help it. Like when we had the producer stop touching the consumer end of the queue and let the consumer only work over here. Reduce false sharing. Alignment is your friend here. To understand scalability, some of the things we did is identify the different kinds of work and measure them, the different kinds of data and measure them, like we did small and large objects, measure total throughput, see how well you scale with more threads, but also see how contention starts to dip that, especially as you hit oversubscription, as you exceed hardware resources. And finally, of course, don't rely too much on tools to draw curves for you. Look at what the data really says. Take one or two more, and then we'll release you to go to the next session. Excellent. Thank you very much for coming. Enjoy the rest of the conference. This is going to be an awesome week. Thank you so much for coming, and enjoy. Have a good night.